Okay, I'm going to try a few more problems from this book on problem-solving strategies, with a particular focus in the first chapter on problems that require finding what the book calls invariants, although sometimes they're quantities that do in fact change, but as you go through some process. But an example of such a quantity that might be useful would be an integer quantity that decreases when you want to prove that a process terminates. I've done several of these questions already. There are 60 exercises on the chapter. I'm not quite sure how many of them I want to work through, but I still feel that there's room to get more out of it in the way of general messages about how to go about solving these questions, rather than just sort of hoping, it's roughly what I'm doing at the moment, hoping that I'll have a bit of luck with each question that comes along, which has been the case for all the questions except one, where I did get quite seriously stuck. And so I approached this task with a little bit of trepidation, just in case that happens again, but we shall see. So let me, I think I say this every time, without further ado, it's a bit of a cliche, share my screen and have a look for the first problem that I've not yet done. And I can't remember what number that was, but I'll soon... I accidentally looked at the page of solutions. Luckily I didn't see any that I had not... two questions I had not done. Okay, so first question I've not done is in the book, question 13. I might as well write 13, even though it's utterly irrelevant. There is an integer in each square of an 8x8 chessboard. Integer in each square of a chessboard. I'm not writing 8x8, I'm just taking it for granted that it's a normal chessboard. In one move, you may choose a 4x4 or a 3x3 square and add 1 to each integer of the chosen square. Just write add 1 throughout that square that you've chosen. Can you always... Oh, wait a minute. Yeah, so can you always get a table? Okay, it's starting to look hard. Particularly if the answer is yes, because there are two parts. With each entry divisible by A 2B 3. Okay, so let's have a look at the 2 case first of all. So can we get a situation where they're all even? Notice in this case that we might as well just work mod 2, so we might as well assume that all the integers are, and all we record is whether you've got an even or an odd, which we can call 0 and 1, and then when we add 1 mod 2. And so we're trying to get noughts everywhere. And adding 1 just means changing everything. So we've got an 8x8 square with a bunch of noughts and 1s. We're allowed to change everything inside a 4x4 square or everything inside a 3x3 square. And the question is, can we get to zeros everywhere? And an immediate... Wait a moment. Yeah, so an immediate observation is that the parity of the number of 1s is not necessarily preserved, because if you've got, for example, 9 1s here, and you change them all to zeros, then the parity of the number of 1s has gone from, let's say it's 0 everywhere else, and it's gone from odd to even. So parity is not preserved, and that suggests that it may well be that you can always get each entry divisible by 2. If you think about it actually for a little bit further, we realize that this is, you could regard this as an enormous system of simultaneous equations over F2. So we have a bunch of vectors. So each vector will be, so if I just draw my chessboard, sorry, it's taking a little bit of time, but it'll be easier to explain what I'm talking about. So I'm considering the vector space over F2 generated by, so to speak, the squares of this chessboard. So if you want to think of it as, if you don't like formal sums of squares, then you can just say that it's generated a standard basis of this vector space. You have a 1 in one square and zeros in all the other squares. And then the vectors that I'm allowed to add are things like 1, 1, 1, 1, 1, 1, 1, 1, 1, or a similar type of vector with a 4 by 4 square. And the question is, can I find, basically do these vectors span the whole space? Because if they do span the whole space, then given any starting arrangement of ones and zeros, I can then subtract that arrangement by subtracting a suitable combination of these vectors. So it's an equivalent question. And we know that the answer is going to be no, if and only if we can find some collection of ones and ones and zeros that is orthogonal to all of these vectors. In other words, a linear functional over F2 from this. That's just from basic linear algebra. So is there such a thing? So that would mean that is equivalent to saying, is there some subset of these squares that intersects all these configurations in an even number of squares? And I suspect that the answer is no. If it were the 4 by 4, then the answer would be yes, you could take the whole square. So maybe just think a little bit about, can you find a subset of the squares that intersects every 3 by 3 square in an even number of squares? And if I just take, so if I take all the black squares, so to speak, then you can have 5 of them. If I take but I have got a little candidate here, actually. What if I take, let's just get rid of those ones. Ugh, got rid of a line as well. I can't really get rid of those ones very easily. So instead of, what if I just take my subset to be squares like this? And I don't know really how oh, sorry, the line got missing, which has now messed up this diagram quite badly. Put a line back in, put a line back in, and 1, 2, 3, 4, 5, 6, 7. Okay, I got the right number. So here's my set. I'm taking alternate squares like that, but I'm not taking these ones, and I'm now taking these ones. I think this is, no, that doesn't work, because I can take 9 squares like that. It only intersects in 1. Is there any other hope for doing this? I think it's going to be hard. So let me now think instead about how I might span everything. I'm coming to think that these 1, 1, 1, 1, 1, 1, 1, 1, 1 things are going to be quite powerful if I want to span. So if I've got this, then I can also, by adding 2 of those 1 slightly shifted, I can also get something that looks like this: 1, 0, 0, 0, 0, 0, 0, 1, 1, 1. If I shift this downwards and add, so I shift it down by 1 and add to what I've got here, then those become zeros. And now I've got a 1, 0, 0, 1. So I've got squares. I've got 4 things like that with that are distance 3 apart, so to speak, or those corners of a 4 by 4 square. that does not yet look that general. I could take a couple of those and then make that 0 and put the ones out to here. But let me see what else I can do with a shift. So if I have 1, 1, 1, and then I shift it diagonally, then I'll have 0, 0, 0, 0, and then 1, 1, 1, 1, 1. And 0, 0, so I've got a thing like that, which is R. If I add to this a 4 by 4 square, I get the bits in between, and if I add the bits in between to this, I don't know whether this is really very useful, but I get 1, 1, 1, 1, 1, and 1, and otherwise 0. But everything I've got looks just a little bit too sort of neat and symmetrical. What I'm trying to do is get something that has support size 1. And that ought to be fairly simple, just because the 3 by 3 square has odd parity, but I'm having a little bit of trouble doing it. What else can I generate? I suppose I can also, if I stick a 3 by 3 and a 4 by 4 together, I can get an L shape like this. So I just use the 3 by 3 to cancel out. So that's all zeros here. If I add that L shape to this, I can get 1, 1, 1, 1. I'm just trying to get things to be simpler and simpler. So if I add 1, 1, 1, 1 to this gadget here, I can convert it into that. And if I add 1, 1, 1, I think we've got 0, 0, 1 there. So if I can cancel out those 3 1s and that 1 there, and just get 1, 1, 0, 1. I'm starting to lose track of whether this is really all 100% correct. But let's keep going with it. And if I've got one of these, I also know that from 2 4 by 4s, I can get a 1 by 1, 1, 1, 1, 1, and then a sort of 1, 1, 1, 1 right down here, where there will be 3 rows in between of zeros. If I add that, then I'll end up with 1, 0, 0, 0, 1. So there's another. I'm getting down to some quite small vectors, but and I've also got to worry about something else which I'm ignoring at the moment, which is what is going to happen at the edges. Is that going to cause me some trouble? And in fact, maybe I should think about that a little bit. Like maybe there's some sort of vector at the edge that will automatically. In fact, I'm gonna have a little try once again at finding something that intersects everything in an even amount. So, because this attempt to produce to generate the standard basis, which If I really wanted to, which I don't, if I really wanted to, I could just write down some horrendous equations and solve them. But I want to, since it seems a little bit unlikely that that's what's required, let's just try again to construct something that will intersect every 3 by 3 in an even amount. So if, for example, I include that square and that square, now if that does fine for this 3 by 3, but not for this one. So if I want to make that one work, I could add in an extra point there. But now this one is messed up. I didn't want to put that in for some reasons, or I haven't. So that means I need to put that one in. Then that one's okay. This one's not okay, so I better put that in. That one is now not okay, but now we can look as though we've got a kind of nice symmetrical arrangement coming up. So let's just fill that in and see what happens. Probably it will be messed up by the 4 by 4s, but maybe I'll be super lucky. Okay, so I think every 3 by 3 intersects in an even amount. Now what about a 4 by 4? 1, 2, 3, 4. If I do that, that's intersects in an even amount. But alas, here is one where it intersects in an odd amount. But can I correct that? I can have a try, but that'll risk, it'll be a big risk that I'll mess up the 3 by 3s. What if I put an extra point here and an extra point here? Okay, I'm now just really experimenting in a rather random sort of way. Right, let's go back and check the 3 by 3s. 4, 4, 3, alas. No, that was not good. So we found an arrangement that intersects every 3 by 3 in an even number. So that all that shows is that I'm going to have to use both 3 by 3s and 4 by 4s if I want to generate everything. But that's sort of interesting because the 3 by 3s, a completely trivial parity argument fails, but this slightly more sophisticated parity argument works. Is there a nicer arrangement, a more sort of natural arrangement that works for 3 by 3s? I think possibly not. But what could I do? If I just put, this is another sort of wild guess really. This isn't going to work for all 3 by 3s, for example. That one's already failed, but let's just put it in and see what we get. So 1, 2, 3, 4, 5. So that's messed up this 4 by 4. But that's maybe it may be okay. Later on, that's also 5. That one's 4, 5, 5, 4, and so on. And if I keep away from the edge, then I've got to include all 4. So now I want to, and then how about the 3 by 3s? I've got this 3 by 3 that I don't really like. So I want to put in a little bit more just to, let's try this. I can't remember whether I've tried an arrangement like this before. Now I've got a 5 here, which is not very nice. And I've got a 3 here. It's also not very nice. and I'm just wildly guessing, which is not great. Somehow a clue with a problem like this is that there should be a reasonably straightforward way of doing it. I suppose I could reduce it to a one-dimensional problem, which may not help at all. But if I were to say, supposing I adopted the attitude that I'm going to fill in entire columns. If I fill in entire columns, then automatically it's going to intersect the 4x4s in an even amount. But each column, 1, 2, 3, 4, 5, 6, 7, 8. So either I fill a column in completely or I don't. But so that means that I've just got to look at 1, 2, 3, or 1, 2, 3, or 1, 2, 3. The number, so what am I saying here? I'm saying if I've got a 3x3 square, like that or something, it's going to intersect each column in an odd number of points. So I can see my way to the answer here, I think. So the arrangement here, which intersected, no, not true. So can I find an arrangement of columns that intersects each, such that each interval of length 3 intersects it in an even amount? I think I should be able to, but let's just see. Let's just be greedy about it. So I'll have those two, then I can't have that one. So I've got to have that one, and then I've got to have that one, and I can't have that one, I've got to have that one, and I've got to have that one. Does that work? It looks very much as though it does work. So here's my solution. I fill in all those, I fill in all those, and I fill in all those. Now I claim that every square, every 4x4 square and every 3x3 square contains an even number of these squares that I filled in. So if I just take some vector that does not contain an even number of these filled in squares, such as just a 1 in one corner and 0 everywhere else, I can't make that vector. And so the problem is solved, although that was only half of question 13. So I've done 13a. Something funny happened there. I just pursued various approaches. I thought I'd just do it by a bit of trial and error. And at some point, and this is a very standard mathematical instinct, but I'm just commenting on it now, just this wish to avoid real unpleasantness kicks in. Sometimes it's worth just trying something not totally unpleasant, and not totally pleasant, I mean, in case you just get lucky. So here I was hoping to get lucky. It looked as though I wasn't going to get lucky, and it looked as though in order to be systematic, it was going to be absolutely horrible. So then that gave me the sort of impetus I needed to think, can I have some idea that simplifies the problem? And I don't, unfortunately, I already, even just sort of a few minutes later, even under 5 minutes later, I'm a little bit like waking up from a dream and you forget the dream after a few minutes. I can't quite see how that nice little idea of just filling in entire columns occurred to me. I remember the words that I said just before. That's, can we do something to simplify the problem? And this was the thing I came up with, but I can't quite remember whether I was using those words after already slightly having had the thought and so on. Anyway, never mind. It's too late to introspect, so I better move on to the next question. What about divisible by 3? So now we have noughts, ones, and twos, and I have a horrible feeling the answer to this one's going to be yes. Horrible, because that seems like a even less pleasant thing to prove than it would have been for 2. In fact, so much so that I think I'd rather try to find a counterexample. So actually, why don't I just try the same trick? So if I put 1s everywhere, that means that the 3 by 3 squares are now completely taken care of. If I have entire columns of ones, but each 4 by 4 square will intersect a column that's filled with ones in a number of squares that is 1 mod 3. So I'm back to looking at the interval, and I would like to find some numbers that will intersect every interval of length 4. Such that the sum of those numbers, each number will be 0, 1 or 2. The sum of those numbers in each interval has got to be 0 mod 3. Actually, that's trivial. I now realize that this was trivial too, because the equations I've got now are in triangular form. When I say 0, I mean I've got to have a non-zero number, but that's fine. So I'll put a 1 there, and then 0, 0. I'm just going to, if I put a 1, I'm going to be sort of greedy. So 0 is whenever I can. And then a forced if I'm forced. So this has got to add up to 0 mod 3, so I'll put a 2. This has got to add up to 0 mod 3, so I'll put a 1. That's got to add up to 0 mod 3, so I'll put a 0. This has got to add up to 0, so I'll put a 0. This has got to add up to 0, so I'll put a 2. How many have I done? 1, 2, 3, 4, 5, 6. I've finished. So I'm putting it as my integers. If I put 1s in the first column, 0s in the second column, 0s in the third column, and so on and so forth, then when I sum up the numbers that I've got in a 3 by 3 square, I will always have 0 mod 3. When I sum up the numbers in a 4 by 4 square, I will always have 0 mod 3. And so now it just remains to find some configuration of integers that when I take this sort of mod 3 inner product with this thing here, I do not get 0, and again I put a 1 in the top left hand corner and 0s everywhere else. I'm not going to be able to make that. So it's a bit of a relief that by the end of that question that, where am I going? Bit of a relief that the answer wasn't yes for either of those, because then I really would have had to show how to generate every single standard unit vector or something like that, and there'd be edge cases to worry about and things like that. But as it happens, I was spared that unpleasantness. And I think I've got time for one more question. That one took quite a long time, but let's just see what question 14 has in store for us. We strike, okay, a fresh sheet. What does this mean? We strike the first digit of the number 7 to the 1996. That gives you a clue when this book might have been published. I better write this. Strike first digit. I presume that just means remove of 7 to the 1996. Either the book was published then or it came from some Olympiad problem that was set in 1996. Let's have a quick look at it. Okay, the book seems to have been published in 1997. It's copyright 1998. Yes, so I think it was maybe when the author was writing this particular part of the book. And add it to the remaining number. Ah, okay. I think I may have seen things like this before, but it slightly depends what the question's going to turn out to be. This is repeated until a number with 10 digits remains. That's quite funny. To a 10-digit number. I wasn't expecting that, I must say. Normally it'd be 1 digit or something. Prove that this number has 2 equal digits. Oh, that's cool. But I think I've seen how to do it, actually. So I would guess that this is a mod 3 or mod 9 question, because if the number does not have 2 equal digits, then the digits are in some order 0, 1, 2, 3 up to 9, and so we can see what the sum of the digits is mod 9. Whether mod 9 is necessary or whether mod 3 will be sufficient, I don't know. But let's just and indeed, if you just take off the first digit and add it to the remaining number, it's going to be preserved mod 3, because because 10 to the 1996, or 10 to any power, is 1 mod 3. So when we remove the first digit, if the first digit is a, we are subtracting a mod 3, and then we add it to the remaining number, we're adding a mod 3. So this is actually not a very interesting question. What is this mod? Let's do it mod 9. So just those add up to 45. So it's 0 mod 9. Not surprising, it could be 9 times 10 over 2. And so what's 7 to the 1996 mod 9? That's the same as 2 to the 1996 mod 9. And can I be bothered to do that sensibly? Let's do mod 3 actually. So yeah, well, 7 is sorry, this was completely trivial. 7 to 1996 is obviously not a multiple of 3 or a multiple of 9. So actually, that was so quick that I think there is time for yet another question. So does that happen before? That any question that's to do with sums of digits and things is not super interesting. Okay, this is looking more promising. There is a checker. Oh, I was thinking of it as somebody who checks things, but perhaps it's a drafts piece or something. There is a checker at point 1, 1 of the lattice. That's weird. I'm going to write the words as in the question, of the lattice, but some of the wording of these questions is a bit strange. Of the lattice xy with xy positive integers. So my immediate reaction when I read a sentence like that is, hang on, xy is not a lattice. So we could put set theoretic brackets. Well, let me just do that. Ugh. I find that such strange wording. I'm going to get rid of it and just call it. And it's not actually positive integers means it's not really a lattice either. But let's forget the words lattice as well. And just the point 1, 1 of n squared. So it's a quadrant of a lattice. Okay, it moves as follows. So clearly this is going to be one of those questions. There are some constraints on how it moves, and we want to show that it can't reach a certain point. That's my guess. At any move, it may double one coordinate, or subtract. I've seen something a bit like this before, the smaller coordinate from the larger. Which points of the lattice can the checker reach? Oh, okay. So it looks as though there'll be two parts to this. Ruling out certain points and then showing that you can get the other ones. It doesn't absolutely say whether you can whether you're allowed to make 0, but if you do make 0, you get a bit stuck. So I think because if, for example, the first coordinate is non-zero and the second coordinate is 0, then subtracting the smaller from the larger makes no difference, and so all that is left to is doubling the first one. So you'll always have a 0 here, and so it won't be an element of n squared. So let's just, I think we will impose the rule, since we would never have an advantage of making a vector with zeros in it. Impose the rule that that smaller means strictly smaller. So if they're equal, you have to double. So let me see whether I can make. It looks as though I can make anything with a 1 because I can just double this 1 as many times as I like and then subtract 1 from the first coordinate. So I can get n1. This is sort of a few little things to discover. And obviously then I can also get 1 n for any n. If I, what about if can I get 2 2? Yes, because I can just double both coordinates. Can I get 3 2? That's the first one that looks slightly less trivial. But yes, I can, because I just get 3 1 and then I double the 1. How about 3 3? Maybe that's more challenging. How would I get that? So I can't on the previous move. So I'm going to go backwards. So the previous move, I can't have doubled something, so I must have subtracted the smaller from the larger, and without loss of generality, therefore it was 6 3. I could have got 6 3 from 3 3, but that I think we can discount because we're trying to get, let's say we got to 3 3 for the first time. So that means this must have come from 9 3. And this can't have resulted from doubling anything. So this 9 3 would have to have come from, so something interesting is happening here. The 9 3 must have come from subtracting the smaller from the larger, so it must have come from 12 3. And again, I could get this from 6 3, but I'm assuming that I don't want to make a loop, so I seem to be forced to 15 3. And from here I'm forced to 18 3, and so on. So it's clear that I can't make 3 3. So there's a. However, that's not a nice invariant type proof. It is a. So actually, if we think about invariants, somehow this is screaming out for highest common factors to be involved. So the highest common factor here is 3, and I wasn't able to stop the highest common factor being 3. And so what? Okay, so we're getting somewhere, because if I subtract the smaller from the larger, that's not going to change the highest common factor. So this is actually a little bit similar to an earlier question. The only thing I can do to the HCF is double it. So we cannot make any number where the highest common factor is not a power of 2. Now this is starting to suggest that we can always make it. So can we always make something when the highest common factor is 1? Because if we can do that, then we can just double both sides. So let's just have another try. Let's do a Fibonacci-ish thing, because that'll be the. Let's try 5 8. I want to get to 5 8. How would I try and do that? Well, I'll maybe go backwards again. Oh, that's easy enough. 5 4, 5 2, 5 1. I know I can do 5. I can do n1, so that wasn't so hard. So anything that's got a power of 2 in it is going to be pretty easy. So what I'm. Yes, so I think I can possibly do this. So if I've got mn, where m is less than n, and m and n are co-prime, then I know that that can arise from m n plus m, which in turn can arise from m n plus 2m, and so on. And if ever I get to a power of 2 here, then I'm in great shape, because then I can just divide it by 2 many, many times, and I get a number of things form m1, which I know I can make. So the question is there automatically going to be a power of 2 that is congruent to n mod m? And that is not a given, unfortunately, because, for example, mod 7, the powers of 2 is not a generator of the multiplicative group mod 7. But nevertheless, this idea feels as though it's somewhat promising. Let me try another one just to get a bit of an inspiration about how to do it. I'll try and get 5, 7. So I could get that from 5, 12, which I could also get from 5, 6. This is looking slightly better, actually. So I could also get that from so I got the 5, 6 because I can double the 6. And 5, 6 comes from 1, 6. Do I mean that? No, I do not mean that. Well, I could do 5, 3, which comes from 8, 3, and then I'm done because I've got a power of 2. So there's a bit more flexibility there, but what was happening? I'll just try one more. 5, 9 comes from 5, 14, comes from 5, 7, comes from, this is sort of strange. So I've got the 5, 7 I already had before. So what am I actually managing to do here? So actually, if I've got an odd number m that's smaller than an even number n, and this is sort of half the cases in a way, because we know that if they're co-prime, at least one of them is odd. So if m is odd, then if I call that n1, if I just keep the m like that, there are two things I can do to n1. I can either add m, or I can divide by 2. So I can go from, so if n1 is odd, I'll replace it by n1 plus m. And if it's even, well, just call it n. And then n over 2 if n is even. So if I just keep repeating that process, it means that n is can't be too much bigger than m. So I suppose that sort of means the kind of cases that I ought to think about are things like 10, 11 or something like that. What would happen there? So that's a slightly unpleasant one because the smaller one is even. but let's just do the process sort of anyway. So I can actually, if the smaller one is even, who cares, just divide by 2. So that comes from 511, and now the smaller one is odd. So actually we can make them both odd. So once the smaller one's odd, I can add a 5 and divide by 2. So I get to 516, and then so put 2 bars there, so that I did 2 things at once. Over 16 is the power of 2. Actually, so let's just put 516 and tick, it goes all the way down to 1. So try another one. 11, 12, no, 11, 13, because we know they're both going to be odd. So 11, 24 goes all the way down to 11, 6. I mean, sorry, all the way down to 11, 3 actually. Now this one's the smaller one. So it's looking as though something's decreasing when I do this. So if I add 3 and divide by 2, yes, okay, I have got something that decreases. So if I have 2 odd numbers, mn, so notice we can always, so I'm doing the whole thing backwards. Instead of trying to get from 1, 1 to mn, I'm trying to get from mn down to 1, 1. I know that I'm assuming that m and n are co-prime because if they have a power of 2, it's hopeless if they've got something that isn't a power of 2 as their highest common factor. If they've got a power of 2 as their highest common factor, well, I can just keep dividing out, dividing by 2 until they're both odd, so we can just ignore that. So m and n are co-prime and both odd. Now, I will at this point apply the following operation. Without loss of generality, m is less than n. I apply the operation, I add m to n, because I know that I can then subtract that m again and get to mn, and then I divide by 2. So mn, I'll just write it in the 2 steps, but I'm going to think of it as a single step. So that's even, and that goes to m plus n over 2. And lo and behold, I've actually got a quantity that decreases because the average of m and n is smaller than n, because m is smaller than n. So let's say if you want what quantity am I talking about that decreases? It's the sum of these 2 numbers. So this process terminates at some point where m and n are equal, but since the highest common factor is preserved during this process, because when we divide by 2 there wasn't a highest common factor of 2, so it doesn't change anything. Highest common factor is preserved. They can only be equal when m and n have got down to 1, 1. So problem solved. And that is enough for this video, I think. So that was an interesting experience. It was one question that was so easy as to be ignored, and 2 questions that I got through, but they took a little bit of time. At some point I might come back and watch what happened in this one. So this was an interesting mixture of experiment and theories. Actually, maybe see if I can try to remember what happened. There were a few moments like noticing that the highest common factor could only ever double when we were going forwards. And in this case, the aha moment was noticing that when we did this operation here, if they started out odd and you added and then divided by 2, actually I suppose I should make the remark that you can divide by more than 2, but if you divide by 2 then still obviously the sum is going down. Something was decreasing, which relied on the fact that n was bigger than m. And that just suddenly, I think that jumped out at me because I was just noticing that when I did this process, things did seem to have a tendency to decrease. And so then it was natural to think, is that really always the case? And it was.